We will now pass to our next speaker, who is Professor Jin Zhou. He is a professor at XJTU in Xi'an in China, and he's working on the impact response of lightweight composite structures. He's an honorary research fellow at the University of Liverpool, and he obtained his PhD there in aerospace composites. He's he's been a research associate working on composite forming in the Department of Engineering at Cambridge University. And prior to returning to academic research at Cambridge, he was a senior structural engineer working on friction welding and structural mechanics in industry for 8 years. His interests include the impact response of composite material, sandwich structures, hybrid metal composite structures, lightweight structures for energy absorption. Jin, are you there? If so.
Okay. Okay, firstly, thank you, Professor Wesley Cantwell. Thanks for introducing myself. And today, it's my great pleasure to introduce my recent research on dynamic loading rate on carbon fiber ring plastic tube structure for energy absorption application. Before I start my presentation, I would like to thank Professor Cantwell and Professor Guan for guidance and help during my PhD study. So it's my great pleasure to share my latest research to both my supervisor, Professor Wesley Cantwell and Professor Zhongwei Guan. Yeah. Professor Wesley Cantwell already introduced my experience. I got my PhD from Liverpool University, and after that, a short academic visit at Imperial College and a 1-year postdoc research at Cambridge University. I joined Xi'an University from 2019. And before that, I also worked in industry for 8 years at Liverpool. Now I would like to introduce my university. It's a leading university in China. So I quickly introduce my university. I think it's a top 10 university in China in engineering and research. We have 5 key laboratories in engineering, and now we have 4 campuses, and the biggest campus is for research hub, and all postgraduate students in new campus and new campus from 2019. So we also have very good research facility to support our research. So this is the outline of my presentation. So today I will focus on energy absorption structure for aerospace and railway train applications. So I would like to introduce 4 structures, include the composite tube and rod reinforced form, composite honeycomb structures, and the composite tube with a tailored fiber layer, and spider web based on carbon fiber ring plastic structure. That's our latest work. And finally, I would like to introduce our project for the railway application. And the third part is just to introduce the latest experiment work on oblique impact on sandwich structures. Yeah, this is the outline. So firstly, I would like to focus on the energy absorption and the dynamic loading rate on those structures. Those structures include the honeycomb structure and the composite reinforced form. And firstly, for the energy absorption structures, I would like to introduce my early research work with supervisor with Professor Wesley Cantwell and Professor Zhongwei Guan. That's composite reinforced form and carbon fiber reinforced plastic honeycomb structures. We did both experiment work and modeling work. We focus on dynamic loading rate on those structures. And later we continue working on the composite tube for energy absorption applications. The carbon fiber ring plastic tubes with a tailored fiber layer increase the energy absorption capacity, and also the dynamic the energy absorption capacity at dynamic loading with a higher capacity compared to the constant loading rate. And the latest structure is the spider web based carbon fiber ring plastic structure. It's very interesting with the new manufacture process. And later I will introduce latest work include the oblique impact on both sandwich structure and fiber metal laminates. That's the outline of my research work. So I will quick go through the introduction. We focus on the lightweight structure because lightweight for in aerospace industry is important, and the potential hazard include birds stack and runway debris and also engine failure. So we focus on impact on composite structures. And the composite was increased application not only aerospace and also the railway high-speed train application. For example, in China, the application of composite is increasing. The picture on the left is the all composite cargo. It's for underground carriage, and that's train speed up to 80 kilo per hour. But the latest train include a high-speed train, the speed up to 600 kilometer per hour. So our research, our latest research focused on the impact loading on those composite structures, and also energy absorber and the high-speed train. That's application in the industry. The background is the first focus on the bird stack. So we did quite a lot of impact tests on sandwich structure for the high-speed train application, and also the composite tube used for energy absorber also have been used in the high-speed train in China. So we got a project focused on developed a new energy absorber for energy application, and the maximal force requires 600 kilonewton, and the energy over 240 kilojoule, and this is the existing absorber, and we focus on developed new structure can have a higher capacity, and the specific energy absorption should over 50 kilojoule per hour. So focus on the latest the demanding our energy absorber. We developed a new structure with a tailored layer. Before I introduce the new structure, I just quick go through our early research work on composite tube reinforced form and honeycomb structures. We did quite a lot of impact test, and we focus on investigate the loading rate effect on those structures. Firstly, we did quite a lot. We did some tests on composite rod and composite tube reinforced form. Those work I completed at Liverpool University with Professor Wesley and Professor Guan, and we found the energy was increased with the core density, and also we get the energy absorption chart against the core density, and also we found the energy absorption against the composite rod diameter and the composite tube diameter. Use this chart, we can develop the new structure for the application for aircraft or high-speed train. We also did a low velocity impact on those structure, and we found that the dynamic and is then and the peak load of those structures increased compared to the quasi-static test, and also the composite tube is the energy absorption of composite tube is increased as well. And this figure shows the stress strain curve of those two structures and dynamic test. And this is a basic test on composite tube. We also did the modeling work and get better correlation against the equipment test. For the composite tube reinforced form, we get this chart for the figure on right shows the energy absorption of those structure with the different composite tube diameter. And the figure on the left hand side shows the dynamic loading rate on the two different structures, the rod system and the composite tube reinforced system. We found that the energy absorption capacity of rod reinforced form was increased compared to the loading at a quasi-static rate, and the tube reinforced form, the energy absorption of tube reinforcement form was reduced compared to quasi-static. And finally, we compared the structure, the rod reinforced form and the tube reinforced form was compared with other structures. And we found the SEA is over 90 kilojoule per kilogram. It's the energy absorption is much higher than other structure for sandwich core. And the latest work we did also we did both quasi-static and impact test on those structures. Those specimen was made in Khalifa University, and my colleague Alia and Professor Cantoner made those sample, and I did a dynamic test, use a drop weight. Initially, we focus on the energy absorption with different layer and also different manufacture processing. And my research focused on the dynamic loading rate on those structures. And those honeycomb form was tested use a drop weight ham. And this is biggest drop weight ham in China, and the energy max the energy absorption up to max the impact energy up to 260 kilojoule, and the velocity up to 20 meter per second, and the maximum height up to 30 meter. So this video shows the low velocity impact on those structures. From the test, we get this video shows the test on 3 different structure based on different composite layers. From this test, we can get the load displacement traces. From the figure on left, we show that the structure crashed at different loading rate from 0.1 millimeter per minute up to 13,000 millimeter per minute. And we also test all 3 different structure and found the compression strength was increased with the test loading rate, and also the specific energy is increased, but it's nearly similar at various loading rate. And the figure on right hand side shows the different show the failure mode of those crashed sample at a different loading rate. And this is the final result shows the structure at show both compression strength and energy absorption of those two structures at different loading rate. And now we move on a new structure because we noticed the composite tube with lower energy absorption at impact loading rate. So we try to improve the performance and get higher energy absorption. So we focus on the nature structure, so we focus on the Bannick design from the nature structure. And this figure shows the microstructure of the hard shell in the nature. And we found those structures, those microstructure, just like a brick. Those fiber not if the fiber not continue, the impact, the energy absorption can be improved. Based on this design, we just cut the continuous fiber to the discontinuous fiber and get a better impact performance. So our composite tube with a tailored composite layer. This is a manufacture process. We cutting the continuous layer to discontinue fiber, and we design. We use pre-plug carbon fiber, and we cut with different gap and different cutting angle to get a different performance. And this figure shows the manufacture process. The pre-plug was a cutting use automatic machine, and we define there is a cutting angle between the cutting direction and the fiber direction, and then we rule out the ruling the pre-plug and use the RTM process to get the composite tube. After Q, we also inspection the microstructure of the tube, and we found in the structure the fiber was cutting. And now we focus on the performance of mechanical properties. We did a similar work. We did a compression test on those structure, and we get we compare the energy absorption of those structure, and we found when the cutting angle up to 45 degrees can get a better performance. And this is a sample with a different cutting angle. The angle from 5 degrees up to 90 degrees, and we found the performance. We summarize the performance and found the energy absorption increase up to 75 degrees. And now we focus on the dynamic loading. We did the same work, use a job tower to crush those samples. And we crush those samples from lower energy to higher energy. The highest energy up to 423 joule on those structures. And the failure mode also showing on the screen. And we compared both the circular tube and the square tubes. And this is a failure mode of those structure. And we can see that the composite tube is crushed to small debris. That means absorbed more energy. And finally, we summarize the energy absorption. We notice that for the normal tube, the constantic the energy absorption at constant rate is higher than energy absorption at a dynamic loading rate. But for the composite tube with discontinuous fiber can achieve a higher energy absorption at a dynamic loading rate. And now we move to a new structure. We try to get when we try to make a bigger composite tube. The tube requires the proper diameter to thickness ratio. If we want to get a better performance of those for the long tube, we need to get a stable. We need to request the tube can be stable during the crash processing. So we just get an idea from the spider web, and also get idea from the microstructure of the beater, and we design a new structure like a spider web, and that parameter include different layer and also different geometric of those structures. The geometric include the diameter of each small tube and the thickness of the wall. And this is the manufacture of the samples. This samples requires the 3 different mode, and each mode is ruling and the structures, and then the whole structure is rolled together. And the mode use a 3D printer, printed the mode. And after curing, we remove the mode and get the structures. And this is a sample with XCT inspection. We just need to make sure this manufacturer can get a lower defect. And this is a geometric design and parametric study. We have different dimension of those structures, include the diameter of a small tube and the length, the distance between the inner tubes, and the other one is the outer distance, the distance between the outer tubes. When we get the parameter, we made a number of samples with different geometric. We test those samples. This is a sample from this sample is different geometric, and we did both constant test and dynamic test. We get this figure show the best 2 samples, the number 6 and number 7, and we can see the maximum peak load is up to 110 kilonewton, and the specific energy absorption is up to 86 kilojoule per kilogram. And we also compared with the normal tube, plant tube, and we found this structure is a better performance with the normal tubes. And use this structure. Those structure, the diameter of those structure up to 60 millimeter in diameter. And now we focus on the application for the high-speed train. The high-speed train requires the structure up to 106 meter in diameter, and requires the minimal peak load up to 600 kilonewton. So we made this composite tubes, and we also use a modeling to simulate the trigger. And the simulation on the right-hand figure is the first case without a chamfer, and the second one and third one is the composite tube, and for the basic with the different chamfer. And we found the composite tube with chamfer have a lower energy absorption capacity. And this is the simulation. Use a finite element modeling, we'll be able to predict the peak load and the energy absorption of those structures. Yeah, and now I just quick show the latest work on the simulation and the experiment work of bird stack. And this is the oblique impact on sandwich structures. And this is the latest test on those structures. And the figure on left is the front camera, and and right is the DSA measurement. From this DSA measurement, we can measure the maximal displacement during impact, and use this data we be able to validate our modeling. And this the DSA output displacement at a different location of the specimen. Using this data, we'll be able to validate our modeling. Use the modeling, we can do further design on those structure. This is the birth stack simulation and sandwich structure for the high-speed train. And we simulate a different oblique angle, impact angle. And finally, we'll be able to use the validated modeling to simulate the impact on the front door and the head of the high-speed train. Yeah, that's oblique impact and the sandwich structure. And finally, we also continue our early work on the oblique impact on fiber metal laminates, and we did a high-speed, we did a high-velocity impact test using gas can, and also did a oblique simulation and use that data to validate modeling. And finally, I would like to make a quick conclusion. And the cutting angle have a significant effect on energy absorption. It's be able to increase the cutting angle from up to 70 degrees, be able to increase the energy absorption up to 74 kilojoule per kilogram. And the energy absorption with tailored composite layer is higher than the plain composite tube with the continuous layer. And we also notice that the energy absorption of sandwich structure at a high oblique impact be able to absorb more energy. And finally, I would like to introduce our research group at Xi'an Jiaotong University, and we also looking for the further collaboration with my colleagues. And finally, I would like to thank all my colleagues and supervisors during my PhD study, and thanks for guidance, and thanks for research collaboration. That's my presentation. Thank you.
Yeah. Thank you so much. That was very interesting, very impressive. We've got a few minutes for questions.
Hi, I have a question to ask Jin. Yeah.
Go ahead, John.
Regarding your high-speed train impact, so you did both testing and the modeling. So is this the structure you suggested or you developed is very effective, or do you need to do any further modification?
I think we didn't make the 4 different structure, and for the sandwich structure we made the 4 different layers, and we will use the test result to validate, make sure the structure be able to pass the test standard.
Okay, so the structure you just showed used quite a big carbon fiber tube, so that's good enough.
Yes, I think for the composite tube, I think that's we did some trial test. The energy absorption is good enough to pass the requirement. They request 240 kilojoule for each composite tube. Okay. The diameter of our tube up to 160 millimeter.
But you still have some foams to support your tubes, is that right?
No foams.
No foams. Okay. Good. Thank you.
Okay. Thank you. I'll just ask a quick question, if that's the case. If you look in the literature, you see that for, let's say, carbon fiber reinforced epoxy tubes, the highest value of specific energy absorption you see quoted is usually about 100 kilojoules per kilogram at a push. The only values that are much higher and well over 150 are on thermoplastic tubes. Will you be able to, or is it possible to manufacture any of these things in, for example, carbon fiber PEEK?
Carbon fiber PEEK.
Yeah, or any thermoplastic really, but high
Thermoplastic. Yeah, we just use thermoset, but we can try to use some plastic. But I think the manufacturer may be more difficult than thermoset.
Yeah, I think that's where the challenge is.
But we can try from we can start from a small diameter tube to test the manufacture process.
Okay, thank you. I don't see any further questions. Thank you very much once more, Professor Jin. That was an excellent talk, very interesting.